So today we are going to start our theories part of our first bit of physics, which is going to be theories of thermal energy. So to start us off, these were actually original theories that they had for heat and understanding what was happening. They didn't understand everything right off the bat. Of course, we figured that out with chemistry. They had to start with some atom theory and they built upon that. So I'm not going to focus a lot on these. Feel free to read through these. I've posted these notes. But basically what we know is we've learned from these scientists and we've moved on. And now what we're going to focus on today is the fact that those were all wrong. And we're going to focus on what we actually know now, which is more correct. And this is what thermal energy actually is. So thermal energy is due to the kinetic energy or movement of particles. So we need to remember that kinetic energy is that movement that all particles are actually doing. Doesn't matter whether it's in a solid, liquid, or a gas. We know that particles are always constantly moving within that substance. So if you think about a glass of water and you think about what we know and look at this little image here, we can see that if we increase the thermal energy or the heat, we are going to actually increase the movement of the particles in that area. So if we increase the temperature in a glass of water, those particles that we can't see are going to actually increase their speed and increase their spaces between them, and it is going to have that energy also increased. These are our two definitions we're going to focus on today. And these are actually right out of your textbook. They should look familiar from Science 7, actually. And what is thermal energy and what is temperature? So thermal energy is the sum of all, pen's not working today, great, is the sum of all the kinetic energy in a substance or a system. So if I am looking for the thermal energy in a substance, I'm looking for the total. And this would be a good little thing to add to your notes. I'm looking for the total amount of the energy. And that energy is always due to the random movement of particles. We cannot predict where particles are always going to move, but we do know that it is always moving. So thermal energy is the total energy, where temperature is the average kinetic energy. So this is not just, you're kind of just looking at what we call the degree of hotness, okay? It is the average. We're looking at all of the particles all together and looking at what if we took all of them, added it up, divided by how many there were, what would that average be? I do not know what's happening with my camera right now. Okay. So to make this a little bit more practical, we are going to look at an example that should be familiar from also grade 7, but I know it's been a long time. So if you have a bucket of water, okay, that bucket of water has particles in it. And then you have a teacup. A teacup is going to have tea in it. It's going to have hot water in it. So if we know the temperature of the teacup is 100 and the temperature of the bucket is 50 degrees Celsius, what would the movement of the water molecules be? Well, in comparison, the pail's particles or the molecules would be moving a lot slower than what the teacup's particles would be going. That temperature means that degree is that how fast are they going. So that degree of hotness, like I told you, is another word for temperature, and it is our preferred word of preferred term. So temperature, in comparison, the bucket would have a much lower temperature, a much lower average kinetic energy, because the particles are on average moving slower, where the particles on average in the teacup are moving much faster. The number of water molecules, well, if you look at even just the size comparison, and if the bucket is full and the teacup is full, which one has more particles in it? Well, if it has more water, it has more particles. So that bucket is going to have significantly more particles than what the teacup is going to have. And this is going to be what influences our thermal energy, because the quantity of hotness, okay, these two things relate to thermal energy. And the thermal energy in the bucket is actually larger because there's so many more particles in it. They might be moving a little slower, but in total, there's way more degrees, quantity of hotness. And the teacup, though they're extremely hot or the temperature is high, because there's less of them, that thermal energy is actually a lot lower. So overall, the bucket has a higher thermal energy. Oh, my pen's shot today. And a lower temperature. And the teacup has a higher temperature and a lower thermal energy. So if I was to give you an analogy of this, we can think about this as if we were thinking about the particles like coins in a piggy bank. So this is one bucket and this is another bucket. So instead of imagining those little dots for particles, imagine coins. So some of the particles are going to be 25 cents and there's 40 of them. So that means in value, this would be $10. The 2 dimes would be 20 cents, and the 3 nickels would be 15 cents, for a total of $10.35 in this piggy bank or bucket. So that is how much there is in regards to particle, where this one has $1 in quarters, 10 cents in dimes, and 5 cents in nickels, for a total of $1.15. Now, if I was to look for the temperature in each piggy bank or in each bucket of water, I am looking at the average kinetic energy. So if I'm calculating average in math terms, I'm going to look at my total and divide by how many there are. So there are 45 coins here. So 40 plus 2 plus 3, so 45 coins. And I should get my average to be 23 cents per coin. Well, this piggy bank doesn't have as many coins, so I'm going to take my total, $1.15, divide by, well, there's only 6 coins, and I should get $1.19, or sorry, 19 cents. So the temperature, the average kinetic energy of each particle or of each coin in this situation, the first piggy bank has actually a slightly higher temperature because the average is slightly higher. Well, the thermal energy is your total. This is average. Well, we've already done the total. In total, this piggy bank compared to the second piggy bank has a much larger total. So therefore, the thermal energy of the first piggy bank is much higher than the second piggy bank. So that is our main concept there. It's our big idea, and the fact that we know that particles are constantly moving, and it doesn't matter whether they are in a solid, liquid, or gas state, that movement is occurring. Okay? Solids are barely, mostly just vibrating. Okay? Now, if you increase their kinetic energy, all of a sudden they can become a liquid, and that liquid, okay, has particles that now start not just vibrating, but they're also rotating. You increase that kinetic energy a little bit more, and that gas now also is translating, so it's moving side to side, and it's also probably rotating, and there's a lot more space between them. So this big idea that particles are constantly in motion and how it relates to temperature and thermal energy is how we're going to continue our learning and concept building on energy overall. And that's where we will be moving on to in physics. If you have any questions, just let me know, guys.